All right, guys. I think this works actually. You got more lights than normal, but can you guys all see this okay? Or do you want the atmosphere to have more lights on? I'm going to take that as an okay. Looks okay. So if you don't have this handout, this is the one that's got 13.3 in the front. Right, and on the back it's got 14.1. We're only going to do through 14.1, by the way. That's all the homework we're going to get started with. This one is the lab handout. So if you haven't had lab yet this week, or if you missed lab, then you want to grab one of these up here. I like it. Okay. So let's get back into this. We just barely started this sequence stuff. I think the very last thing we looked at was that nifty Fibonacci sequence. Threw a little extra stuff at you. And if you Google Fibonacci and then almost anything, Fibonacci music, Fibonacci surfing, Fibonacci food, there's going to be some connection. It's great. Fibonacci art especially, because it has a lot to do with what's aesthetically pleasing to us as humans. It's kind of nifty. This is the very last stuff we'll do, the sequences and series stuff. We sort of got into it last time, but now we're going to get a little bit deeper into it. So this one is this one. So we already sort of know the idea behind this. So when you're thinking about a formula for AN, let me ask you this. What does your gut tell you A1 is up here? What's A1? 1. So A1 is the first term in the sequence. It's crazy. So A2 is 4. Do you see a connection between the term I'm talking about and the number that's the output for it? 1, 1, 2, 4, 3, 9. So can I come up, AN would be based on N, and what is it that I do to the subscript to figure out what the term is? I just square it. So that is the formula to figure out any term in that sequence. So what would A10 be? Yeah, A10 would be 10 squared. 111. Cool. So it's exactly like function notation, where n is the input. But what I'm getting out of that function notation is what the term in the sequence is. So if there's a pattern to a sequence, I should be able to capture that in an equation. So then I don't have to write all the terms out to get the 80th term. I should be able to just plug an 80 into some equation to figure out what it is. I mean, on the surface of it, that's what math does. It finds patterns and then simplifies things using that pattern. The rest of these questions are a little less tricky. Let me see if you guys can do number 2 here. This guy. If you don't have this handout, come up and get it. So what's A1? Yeah, it's 1 times 1 plus 1. 1 times 2 is 2. It's crazy. A2 would be 2 times 2 plus 1. You guys see how it's just like function notation? So it's really just taking that number and plugging it in. So 2 times 3, 6. Crazy. A 3, 3 times 3 plus 1, 12. And 4 times 4 plus 1, 1. All right. So what would A8 be? Yeah, it would be 8 times 8 plus 1. 8 times 9 is 72. Are you guys, is everybody cool with this? I mean, this is, function notation got you ready for this. I can use the idea of substitution in more than just that direct way. I can construct sequences. And that seems like something you would just do if you're really, really bored and you wanted to pass some time. But sequences are unbelievably useful to know how to construct them. What about A20? Yeah, 20 times 20 plus 1. 420. Good. So you guys want to get that? Let me see. And then number 3, same way. So when you see the little a subscript, the little a with a subscript, that means sequence elements, terms in a sequence. We're going to see the next level of this would be the sums of the terms in a sequence. That's the next level. Amazingly enough, we're going to use the letter S for that. So what about this guy? What's the first term in this sequence here?
1 over 1.
Yeah, 1 over 1. Just let n be 1 to figure out the first term. A2 would be, amazingly enough, A3 would be, A4 would be. You can't beat that. The only way to beat that is to say an equals n. A10 would be,
1 over 10.
holy shit. What's A 2017 just to do that?
1 over 2017.
I like it. So like a year ago. Okay, I like it. Please don't let this be difficult. That on the surface of it, it really is just plugging values in for n. You should be very, very used to that. You guys do this one. Okay, so what's A1?
5.
5. What's A2?
8.
8. A3?
11.
Crazy. A4?
14.
14. Now, can somebody just tell me in words the very quick way to express the pattern in this sequence? Just keep adding 3. Do you see how it was captured here? This is, on the surface, it seems kind of counterintuitive. I keep adding 3, but how is it represented in this sequence? I multiply n by 3. Well, why does that make sense? Because if I start here and I take 1 step, that's 3. I take another step, that's 2 3s, 6. Take another step, that's 3 3s, 9, right? And doesn't that sound like slope? Take a step, and then how much does the output change? Take a step, and then how much does the output change? That's slope. So that's why this is the equation of a line. I have a place I start. Now what's really weird, let me see if you guys can get this, because this will help out with something you have to do in lab, if you haven't done this yet. This is going to seem a little bit weird. This doesn't always work. But what would A0 must have been? What must A0? In fact, you can plug a 0 in and see it's 2, but isn't it like go back 3? So see, A0 would be the y-intercept. That's where you start. And then the slope tells you how much you change that by for every step you take. So if I start at 2, take 1 step, that's not going to be 5, and so forth. I like it. So if you keep adding 3, it's going to end up being 3n plus something in the equation form of that. I like it. And then these are easy enough, right? Just gotta plug those things in. What do you plug in for this guy?
29.
Yeah, you plug in 9. 3 times 9, 27 plus 2 is 29. That's crazy. And then here you plug in 100. 302. It's crazy. So real quick, let me see if you guys can get this done. So what if I had this sequence here? 4, 9, 14, 19, 24. What would A-N be? A-N. Yeah, what is it that I keep adding? Every step I take, it gets how much bigger? 5. So I'm going to have a 5N. Now it's not plus 4. It's plus what A0 would have been. Yes. So if you go back 5, you go to -1. So it's going to be 5N minus 1. How do I check that? What's A1 by the formula? It would be 5 times 1 minus 1. It's 4. Check. What's A2? It would be 5 times 2 minus 1. Get out of there. Thinking ahead, Jeff. 10 minus 1, 9. Check. So whenever they ask you to put together what AN is, you can always check it. You just plug in 1 for the first term, make sure it actually comes out to be what it's supposed to be. Okay, I like it. So here's the next kind of logical step to take. And that would be, okay, once we get a bunch of numbers just separated by commas, I'm curious if there's patterns within the sums of those numbers. So if I keep going forever, so if I have an infinitely long series, it's called an infinite series. It's pretty. So a sequence is this. A sequence is numbers separated by commas. So they have terms, and I can figure out a formula to get each term, so forth. Is that cool? A series is just taking the terms of a sequence and adding them up. We call that a series then. So it's having a sequence, but adding up the terms. So, for example, can you write the first 4 terms of this for me? Because this symbol here is asking for the sum of the first 4 terms. That's what that symbol means. The sum of the first 4. A4 would be the 4th term. S4 is the sum of the first 4 terms. So you just figure out what the first 4 terms are, and then you add them up. That's crazy. Almost too nice to believe. And they use a little s. Holy shit. That's awesome. Just in case you came in a little bit after we did some of these. A1, how do I figure that out? How do I figure it out? Plug a 1 in for n. It's crazy. So I get 3. A2 is 7. A3. Now you should. What's the pattern? They keep going up by 4. So the next one should be 11. If you check it, it is. And then 4th one will be 15. If you check it, it is. So S4 would just be to add those up. The sum of the first 4 terms. Yeah, so 10, 26, 36. That's S4. If I said S7, you just figure out the next 3 terms and then add all of these up. I like it. I just gave you one of these. Let me give you another one. Let's see. Let's do this one here. That's nice. I like that. Very gentle and calming. Sorry. So find S3 for that sequence. Given the sequence, find S3. If you didn't get this handout, then you probably should come get it. And there's also one from the lab. So if you missed labs this week, or if you're in the next lab, you're going to want to take this last one too. By the way, real quick, today's the last day we're doing new stuff. Yeah. Tomorrow and Thursday will be devoted to review. There's this worksheet we did in lab. I'm going to talk about that tomorrow in class, in lecture. I'm going to have another handout tomorrow and Thursday in the labs for some extra practice from like earlier in the semester too. And you get the practice final in the labs if you come to lab. If you don't come to lab, then oh well, you didn't want it. That's your choice. So what do I have to do first for this? What does this symbol mean? Sum of the first three. The sum of the first three. So I got to figure out what the first three terms are. So what's A1? 1. What's A2? Right? Because if you plug a 1 in, you get 2 minus 1. A2 would be 2 times 2 squared. 2 times 4 is 8. Minus 2, 6. Pretty cool with that? Let me just write out A3, just make sure everybody's cool with that. A3 would be 2 times 3 squared minus 3, right? Plug a 3 in for n. So we get 2 times 9, 18. Minus 3 is 15. So here S3 would be 1 plus 6 plus 15. 22. I like it. So if I said find the first three terms of the sequence, it would be 1, comma 6, comma 15. If I say find S3, that's 1 plus 6 plus 15. So a sequence has commas, a series has plus signs, and then you actually do it. That's why we call one a sequence and one a series. They are connected, but they're not the same. Okay. Now, yes. Now, let me give you this guy. This is the last new material. Oh my God. I love that some of you guys told me. Now, real quick, I want to point out here's the new information. I decided to go and just throw this on there so I didn't have to print it out in addition to or whatever. Just to remind you guys, Tuesday, so a week from today, is our final, which is kind of nice to be honest. It kind of sucks to have I have Monday, June 4th is my other two finals. So it's a long time between the last time I see them and the final. Oh shit. I am in my office right before that. Okay? Starts at 9:25, which is nice for you guys. Because we normally start at 9, so you can't go wrong. My Math 160, we normally start at 12:30, and the final starts at 11:35, and I know that a few of them are going to come at 12:30. So they have decided to have an hour less for the final. I am in the office other times. I am actually, and Monday I got other stuff, but I figure this is going to be far enough. If you, when you take the final, you can email me. I can tell you how everything kind of shook out. If you need to come see me, you can come then to see any specifics about your grade stuff. You guys with me? Okay, cool. So that's the plan for next week. Next week there are no classes. No classes. It's all finals. All the schedules should change a bit. All right? So be really careful that you don't have a final. Make sure what time it starts. If you have a final, it doesn't start the exact same time as normal. All right? Okay. So let's come back here. So that idea we just did, that partial sums idea, the sum or the first 4, first 7, or whatever, we need to be able to control that better. Some of you guys have seen this before. This shows up in statistics. This shows up in, could show up in a lot of different places, to be honest. How many of you guys have ever seen this symbol besides related to a sorority or fraternity? Right? I'm going to pledge to sing a symbol. Yeah. Yeah. Okay. Where'd you see it?
A lot of TV shows.
Oh, a lot of TV shows. I like it. So it's out in the wild. That's good to hear. This is the Greek letter S, capital letter S. And they chose it because they're like, let's use Greek because it looks really nifty, and let's use S because it's a sum that we're talking about. And they're like, that makes sense. So there it is. Now, a lot of mathematics is all about what the hell does the symbol mean? What is it asking me? We've seen that, like log. What is it asking me? If you can internalize the question, those questions are easy. Just like a square root, what's it asking me? So, what is this asking me? This is asking me to sum up the terms of the sequence from the second to the sixth term. So this would be A2 plus A3 plus A4 plus A5 plus A6. So I can be a lot more specific than just saying S6. S6 would be from the first to the sixth, always. This notation lets me be more specific about just what part of it that I want to add. I like it. Now what some of you guys have to realize is this is used in a ton of different places. Holy shit. What we're not going to have time to do is to get into a lot of those different uses. This is just the nuts and bolts of how the hell this thing works. So I know before you see the uses, very often you're sitting there going, well, they're just playing around with frickin' numbers and putting Greek shit in there. But there is a purpose to this, and this is the point where you first kind of see it normally, right? So let's get specific here. Wow. So on one level, this is like the A stuff and the S stuff put together. What does this symbol ask me to do? What is it asking me to do? I want to sum up these from the first term to the fourth term. So I want to let K be 1, 2, 3, up to 4. So this tells you from what to what. And they only are integers, right? And actually they're natural numbers, to be honest. But so how would I set this up then? If K is 1, what do I get?
1/4.
Yeah, so 1 squared plus, now you let K be 2. 2 squared plus, let K be 3. 3 squared, now to let K be 4. 4 squared, and then you do it. 1 plus 4 plus 9 plus 16, which is 30. I like it. Okay, cool. You guys try the next two. Be really careful about this negative on number 3. Sean, did you get those two done? You got it? Cool. Alright guys, what do we got here? When k is 0, what do I get here? Negative 1. Plus, this is all about adding. That's a Greek letter S, sum, it's all about adding. So the first term I get is when I plug a 0 in. Now I'm going to plug a 1 in, because I want to go from 0 up to 3. So when I plug a 1 in, I get 3 times 1 minus 1 is 3 minus 1 is 2. Plus, now I want to plug a 2 in. 3 times 2 is 6 minus 1 is 5. So you can even, if you want to, this is k equals 0, this is k equals 1, this is k equals 2, right? You kind of make little notes for yourself so you don't miss anybody. And then if I let k be 3, I'll be done making sequence elements, right? Like k be 3, I get what in here? 3 times 3 minus 1, 8. And you notice how they keep going up by 3. That's what this sequence definition tells you happens. Slope of 3. And then you just got to add those up. 14. Chibam. All right. You guys get number 3 yet? Yes, ma'am.
Why did you do 4 numbers when it says 3?
No, it says let k go from 0 to 3. 0, 1, 2. Oh shit. Yeah. Real careful. That top number doesn't tell you how many numbers you should end up with. It tells you which term should you stop at. Yeah. Is that cool? So you plug k equal 3, 4, 5 in. What's negative 2 cubed? Negative 8. Negative 2 to the 4th power. Positive 16. Negative 2 to the 5th power. Negative 32. I like it. Good. So you should end up with negative 24. Cool. I like it. This is not bad. Relative to some of the stuff we've done. All right? It's not a bad place to end up. All right, well, here's where it gets a little bit more interesting. These are nice because they give us the equation already. It's always a little bit easier situation. We just got to plug stuff in. The next two are where we have to figure out what the equation must have been. So what you're looking for is the pattern. Can anybody see it? Now, the top pattern is easy as hell. The top pattern is, it's always 1. The top is always 1. You guys with me? So I know this is going to be the sum of 1 over something. I mean, it's always freaking 1. What's the pattern on the bottom? Yeah, I keep multiplying that thing by 2. So this is 1, 2, right? This is 2 to the first. 4 is 2 squared. 8 is 2 cubed. 6 is 2, 4. So where is the part that is changing in every term? The power. So the power is the part that's changing. That's going to have to be where the k goes. And to be honest, the letter we use, it could be I, J, or K. That's the ones that we normally use with summations, I, J, K. Just like with algebra, it's X, Y, Z's, the primary ones we use. So what do I put on the bottom? What part of this stays the same that the 2 does, right? Now if I put a K here, this is where you have some flexibility. If I put a K here, where's K start? 1. Up to what? 4. But you could put like a K plus 1 or K minus 1 and have it start somewhere else. I mean, you have a little flexibility there, but I always try to go for the simplest way of writing it. Yes, sir?
Could you write 2 to the power of negative 1?
Beautiful. I love it. Yeah, it's the same thing, right? 2 to the negative K is 1 over 2 to the K. Just flips it. Sweet. You guys try part B. Again, what's changing, what's staying the same. That's what you look for to start with. So try 4B there. Yeah, always hopeful. I call this my hopeful Tai Chi.
He's a ruler.
What's it mean?
Ruler.
Ruler? That's awesome. It's mathematically related. That kicks ass. Sean, do you have that done? Sean, do you have that done? 4B?
It's not exactly what I expected. I was saying 2258 or something. 2258 or something. I don't know what I'm looking for.
So what stays the same? The power. So I know there's going to be a 4 there. That doesn't change. So I don't want to put a variable there because it stays the same. What changes, of course, is the base. Starts at 3, goes to 6 in a nice orderly fashion. Do you see how that's just screaming out that that's going to be what? What am I going to put what to the 4th power? K. Then I go back. So that's basically what I do first. I figure out what that form is, and then I go back and say, okay, now I can control where I start and where I end. Where do I want to start? Freaking 3. So that's the first thing. And where do I want to end?
6.
Freaking 6. All right. So you notice you look for what's changing and what's staying the same. Now, is it always going to be as obvious as that? No. But I'm not going to give you anything over the top, because it's the last thing we're doing, and we're not doing it for very long, so I can't really throw some weird shit at you. All right, so let's try these. Try these next 3. This is a little overall review of this. Oh, yeah, I'm gonna let them work for a little
We're
bit.
short staffed today.
I understand.
Everybody's sick.
Yikes.
So I'll be back.
Anybody else need this handout we're working on? Say again? Yes. Yes. That's what that evaluate part means. Yeah, skip them instructions, man. That's sort of like the way I used to do video games. Plot that thing in, screw the manual. It's like the Denny's approach. What the? Just for late at night and when you're drunk. Good things. Okay, let's see. Catch up to you guys. So this first one, I'm going to let K be 0 first. 0 plus 2 to the 1 plus 2 squared plus 2. And that tells me to stop there. So officially this is called a partial sum. It's the same thing that little s did for me. So this will be 1 plus 2 plus 4 plus 8. 15. If you're really kind of taking this in a little bit, you should realize, oh my God, this is nice. Here, start with k equal to 3, and what do you get where k equals 3? You get 2 times 3 over 3 minus 2, you get 6 over 1.
I didn't see that, sorry.
Here on top. And then let k be 4, 8 over 2, I like it. And let k be 5, 10 over 3. Oh, that's too bad. You're so excited. Oh, 6. Oh, 4. Oh, 10. Shit. What is 10 thirds is a mixed number? 3 1/3, right? 9 thirds is 3. And this is 9 plus 1/3, so it's 3 1/3. So it's 10 plus 3 1/3, which is 13 1/3. Or 40 thirds. I like that better. Okay. And then this guy, same idea. Let KB 3, and you get what? Yeah, you get 12 plus 5, 17. Like KB 4, and you get 16 plus 5 is 21. Like KB 5, 4 times 5 is 20 plus 5 is 25. And like KB 6, 24 plus 5 is 29. Some of you guys might also realize, again, this is a line, right? So once I know the first number, it's going to increase by 4 every step, because I take k steps. So every step I take, I increase by 4. And if I add these together, these are 50. These are 42, 92. Not too bad. All right, do the last one. You said numbers.
Yeah.
Numbers? Nobody told me they read numbers. Damn, math class. Dates. In history class. What the hell? So what's really nice, what you should do for yourself is to rewrite this. Yeah, so 25 is 5 squared, 36 squared, 7 squared, 8 squared, 9 squared, 10 squared. So this will be the sum. Now here's the situation where I know where I want to start and end already. Where do I want K to start? 5. And I want K to go to 10. K squared. Now real quick, last thing I want to show you. There do exist in mathematics, there do exist urban legends. They are not anything you want to make a movie out of, but there is one urban legend about a man named Gauss and his teacher when they were in like, the equivalent of second grade or something. The teacher's going crazy. He said, all right, add up the numbers 1 through 100. And when you're done, let me know. I'm going to sit here and take a nap. Right? So, I mean, if you're going to add these up, how would you do it? 1 plus 2 is 3. 3 plus 3 is 6. 6 plus 4 is 10. It's going to take you a while, right? This is what he was banking on. You guys kind of with me? He was banking on this taking them a while. Gauss supposedly got done in like 7 seconds. Not because he's able to add very quickly, but because he can notice patterns, right? Or he could. Gauss did too much stuff. Come on, Gauss, leave some shit for somebody else. But notice this. What's 1 plus 100? What's 2 plus 99? What's 3 plus 98? How many 101s am I going to have? 50 pairs make a 101. I have 100 total numbers, so I'm going to have 50 pairs of 101. 50-50 is freaky as shit. The first 100 natural numbers add up to be 50-50. That is interesting. Right? At least on some level. But that's there's a whole thing about this. This is what's called an arithmetic sequence, and this is how you can add any So anything that, like 2, 5, you can keep going, Jeff. 8, 11, 14. If you have any sequence where it just keeps adding the same number, you can do the exact same thing I just did. Right, so to add these up, I can do 16, 16. Now this is funny, that's 8, I know. And let me make one more, just so it doesn't get all freaky. 19, 19, 19. 3 19s. 3 20s is 60, so 3 19s is 3 less is 57. So those add up to be 57. Kind of a neat little trick. All right. That's plenty. So I'll see some of you guys in lab. If you want to practice final, you should probably go there. possible. That's my time. What time is your religion class doing? No. So what do you?